Hello, everybody. I think you can hear me. I see some waving. Thank you for with your response. We're going to start off with attendance. Please put in the chat which of your skills are you most proud of? You have a lot of skills. You're at this point in your lives, which means you have a lot of skills. So, what are you most proud of in the chat window for the attendance today? We're going to also look at the assignments coming up this week and just stuff happening this week in the lecture portion of the class. This week we are talking about, we're finishing up uncertainty propagation and also covering mean and standard deviation. And I have all the reading assignments posted now for the semester. So there's a specific set of pages from Taylor that you should be reading for your to prepare yourself for lecture and just to reinforce what we're doing in lecture. Okay, and we also have homework 2 that's due on Thursday, the 11th. You are making plots, and you're going to use Python to make plots. Just a little feedback from the previous graph assignment. Some people submitted a connect the dots sort of looking plot, which is what I did at first because I kind of just like followed the tutorial. But then I looked at that and I was like, I really want to see those data points. I don't want to see this like line or whatever, this curve, this red thing. I want to see individual data points on my graph. So I went and Googled, I can't remember what I Googled, Python data points, like show data points or something. And I found another command like pretty easily, like a scatter plot command, that instead of whatever the command was to plot from the tutorial, I used this other scatter plot command. I'll post my version on the As You Learn page. But it allowed me to view those points individually. So when you're turning in this homework, I expect you to use everything we learned in class. Like, you shouldn't connect the dots. You should show the individual data points. Any questions about that homework? Homework 2 or reading assignment?
So are you saying we shouldn't do a line of best fit, or we shouldn't do a line that connects all the dots?
Oh yeah, okay, thank you, Brendan. You should do a fit if you can and if you're asked to. A fit is always great. You should not connect the dots unless there's a reason to connect the dots. But that's probably not going to happen in this homework assignment. Like later on, there are really later on in your physics career at App State, you're going to have to plot things that are more complicated. And sometimes the reader just needs like a guide to see what the points are doing based on like a model maybe. But then you have to explain that. If that's what you're doing, if you're connecting the dots for some reason, you explain what you're doing and say it's not a fit. Brendan, does that make sense? Did I answer your question?
Yeah, that makes sense.
Okay.
Thank you.
Sure. Oops. Okay. Okay, so yeah, I have been able to talk a little bit to Dr. Chandra and also Dr. Burris about lab stuff, lab things y'all have been asking about. And it looks like Dr. Chandra's already kind of had a plan to make things more straightforward, but also he, it's probably my fault that I didn't encourage you all to go talk to him directly. So I'm sorry I failed you in that respect. It really is going to be best if y'all could directly tell him what exactly is confusing, what is not clear. And then he can fix those particular things. And I'm happy to still continue to, help make that communication happen. But please do, he really does want to, he wants you to learn. He wants to teach you effectively. So he wants to hear your feedback. So I encourage y'all to talk to him directly and keep, communicating with him, keep communicating with me. He and I are going to be meeting weekly so he can see what I'm doing in class and I can see what he's doing in class. And we're really trying to coordinate so that you learn what you need in lecture before lab and vice versa, if it happens that way. Any feedback on that or questions?
Can you hear me?
What's that?
Can you hear me?
Yes, I can hear you.
Are we going to go over how to write in an AIP style or in this lecture class or not?
I had not planned to go over that, but I would be happy to do a special student support session on AIP format if you'd like.
Yeah, that would be pretty great.
Okay, we can do that tomorrow and I'll record it for people who can't be there. Put it on the As You Learn page.
Okay, thank you.
Sure, keep sending requests like that or asking questions like that. Thank you, Tristan. Any other questions or feedback or anything else about the class in general?
I talked to Dr. Chandra a little yesterday, and I'm going to keep talking to him, Dr. Hester. So I just
Great.
want to let you know that because
Awesome.
I told Dr. Burris, but since I probably should have just sent that email to her, but yeah.
Well, I should have encouraged that. So shoulda, woulda, coulda. We're just learning, we're physicists and we fail over and over. And this is what we do. This is also not just in the lab, but like in interactions with humans. So we'll learn from it and we'll move on and we'll keep communicating. But thank you all for being open and, and doing the communicating. It's gonna help solve some frustrations for y'all, I hope. Okay, why do I care about uncertainty? Remind me.
If we want to be honest about our lab results with ourselves and with communicating them, then we have to recognize the fact that they're not perfect.
Yes. Okay. Yes, what else? There's a particular point that I haven't really touched on yet that I want to definitely touch on with another reason why I care about uncertainty. So what else? Anybody else have another way of saying Sorry, go ahead.
Anything that we measure isn't going to be perfect, so we have to have the uncertainty because it could vary between measurements or instruments, and if somebody else were to perform the experiment, they might get a different one with an uncertainty. So as long as they kind of like fall in the same general area, then they're usually good values.
Yes. Okay. What else? Anything else?
Uncertainty also helps with telling how accurate or precise our measurements are.
Okay, with both?
What was that?
With both accurate and precise?
Yeah.
Okay. So our uncertainty is going to tell us how, a range of incorrectness we should expect to come across. But if we do our experiment completely wrong in the first place, we're going to get inaccurate results even if we have really good precision. If we have like awesome uncertainty, but we use the oscilloscope wrong somehow, we're not going to have a correct outcome, and our precision isn't going to be able to explain that. Our uncertainty isn't going to be able to explain that. So thank you for saying that, because that's what I was trying to touch on. In the end, when we measure our speed of light, we're going to continue this analogy. If I measure the speed of light and compare it to the known speed of light, the accepted speed of light, and it's wrong, there's a lot of reasons why it might be wrong. One reason is my uncertainty. So the uncertainty helps explain the error. In addition to us knowing how correct we should be based on our precision and our measurement uncertainties, we also can then explain why our final value is not correct. It's going to be from the precision plus other things, like maybe I did the experiment wrong. Maybe the temperature was changing in the room. And those things don't really have anything to do with uncertainty. All right, we'll keep talking about this. Let me know if you have anything to add while we transition to looking at some slides here. Okay, I'm just going to quickly review what we have already talked about regarding propagation of uncertainty. All right, can y'all see my propagation of uncertainty slide there? Yes, cool. All right. Let's remember what we have learned here. If we measure x, y, and z, and q is equal to a sum or difference of x and y and z, then the uncertainty in q is going to be the sum of the squares of the uncertainties, the square root of the sum of the squares of the uncertainties of the individual measurements. Okay. If we multiply instead these measured quantities, we measure x, y, and z. Whoa. Okay, sorry. If we measure x, y, and z and we multiply by a constant, we multiply x or y or z by a constant, like capital B is our constant here, then the uncertainty in q, the uncertainty in our final value, q, is going to be the uncertainty of our measured value x times that constant. But if we're thinking in terms of fractional uncertainties, the constant is in the numerator and denominator, and so it cancels out and does not matter. Okay, more review. If we multiply or divide our measured values x, y, and z to get q, then we think of fractional uncertainties in that case, mostly to help us not have to deal with units. We can think of percentages instead of units, basically. So if q is xy divided by z, then the uncertainty in q divided by q is going to be the square root of the sum of the squares of the fractional uncertainties, the individual fractional uncertainties. Okay. We did this one too, I think. If we measure x, we measure y, we measure z, and we raise x or y or z to a constant, not integer, gosh. sorry, constant n to get q, then again, we think of fractional uncertainties, but the fractional uncertainty of the final q is equal to the fractional uncertainty of the measured quantity times that constant. Absolute values. Okay. There are some problems posted on the As You Learn page. If you go to this week, the in-class problems 2-9. Okay, I want you to click on that, and the problem, we already did parts A and B of this first problem. I want you to do C, D, and E. Okay, of problem, whatever, no, you know, the first one listed here. I will open up breakout rooms and put in the chat who you're supposed to be in your breakout room with, and you can all access these problems on the As You Learn page. Here we go. Get started on those while I'm opening up breakout rooms. So C, D, and E of the first problem listed on that sheet. All right. Okay, all the rooms have been opened. You should be able to go to your particular breakout room that's in the chat. Okay, welcome back, everybody. I am displaying the problem here in my screen share. And the idea was to complete C, D, and E, hopefully in your breakout rooms. If you didn't complete it, whatever, it's okay. Does anybody want to try to give me an answer for C? Or I can call
I'll go.
Okay, cool. Thank you, Sean.
I got x equals 0.0016 plus or minus 0.0002 centimeters.
X equals, say that again. Can you hold it up or something? You have it written down?
It's that one.
Okay. So you were supposed to find the fractional uncertainty or the percent uncertainty.
Oh,
Right?
I thought we were just supposed to get like the full thing.
On the percent uncertainty.
The percent uncertainty
Yeah,
would be
I think
10%.
we should have about the same. I'm displaying my solution up here for those who want to try to compare. So I rewrote x as x equals u to the -2 because I don't like denominators. If I don't have to have them. And then we know our rule regarding constants, or sorry, our rule regarding exponents, like our measured value to an exponent, means that we put that exponent in the front of the fractional uncertainty for that measured quantity to get the fractional uncertainty of the calculated quantity. So that's what I did here. We are told the uncertainty for U was 2 centimeters and for V was 0.5 centimeters. And so I substitute here 2 centimeters for delta U, the uncertainty in U, and 25 centimeters for the uncertainty or for the measured value U, and got 0.16, which really should have been 0.2 based on the sig figs. So I really probably should have had a 20% here, but it's kind of on the borderline of making the value much bigger by rounding to the 1 sig fig. So in this case, I left it as 2 sig figs. Is that what you got, Sean, kind of?
I'm kind of confused. So for if it's just a fraction, so it's like the fractional uncertainty of x would equal the absolute value of n times the fractional uncertainty of u, right?
Mm-hmm.
So the fractional uncertainty of u is 5%.
Delta U over U.
Yeah, so you can just put 0.05.
Mhm.
So then
Yep.
that times 2 would just be 0.1.
So, yeah,
I-
I know where the problem is. You can go, Henry, if you want.
Yeah, so the difference is that she found her uncertainty, her fractional uncertainty for U, which is like 1.25, and then rounded that up to 2 centimeters, and then used that uncertainty instead of just the fractional.
Oh yeah, sorry. I guess we should back up. Let's back up here.
Yeah, and that's
Where
what
did, where did
confused me
those
about it.
uncertainties come from? Sorry. So we backed up to where did the uncertainties come from? We were told in the problem that the manual states that the percent uncertainty for the measurements is 5%. Yes. Okay. And then we know that the measurement for U is 25.0 centimeters and the measurement for V is 10.0 centimeters. So the uncertainty for U is going to be 5% times 25 centimeters, which is 1.25 centimeters, but I should only have 1 sig fig for my delta U. So I rounded that up to 2 centimeters. And then same thing for delta V. Well, that one already was just 1 sig fig.
Would it be inaccurate to continue and use the 5% as the fractional uncertainty without having to calculate what the actual uncertainty is?
Do you mean substitute 5% times 25.0 centimeters in for delta U everywhere? Well-
When not delta U, when you have like a fractional uncertainty, so like delta U divided by U, rather than doing 2 over 25, would it be wrong to do 0.05?
Would it be wrong to have 1.25 over
Here, I'll just look at it.
25? I think it's probably, you know, if you're never sure what to do, you choose the safer option. And the safer option here is going to be where we round up first.
Yeah.
So that's going to be the one where we're more, if we choose that option instead of keeping the, you know, the 5% times 25.0 centimeters throughout as our delta U, we will have a more safe, a more conservative estimation of our uncertainty, but it's not incorrect to do it the other way either.
Yeah.
I think either way is correct.
All right. Okay. Thank you.
Mm-hmm.
So I'm sorry, I'm still a little bit confused. So what I did was just put 0.05 as the fractional uncertainty for U inside the absolute value and just multiplied that by 2. So then it's just 0.1. So then it's 10%. I'm confused why that's not right.
Well, it would be right, but this is safer, I guess you could say.
Oh,
It's more appropriate to do.
Yeah, I'm
Okay.
calculating 16%, which would actually round up to 20% if I was using my sig figs correct. So my estimate is more conservative than yours, but we can explain either way. We can explain how we came at that answer and have 2 different answers, and that's okay.
okay.
Other questions? Comments? Thank you, Sean. Who wants to try D? We have a product and we have an exponent. Did anybody get a result for D?
I did D like how Sean did C, so mine is like smaller than what you would normally get.
Okay,
I got 12%, which would be like the lower bound, I guess. But if you actually,
12%.
yeah, but if you actually put it in like 2 divided by 25 and things like that, it's going to be a bit
Yeah,
bigger.
I got 13%. So
Yeah.
pretty close. So we probably did basically the same procedure. Let me know if this doesn't look like what you did, Abdel.
No, this looks the same.
Okay. So we're finding the fractional uncertainty of x. Oops, sorry. So we're going to take the square root of the sums of the squares of the fractional uncertainties of u and of v squared. So we're taking the first part of the product, u, and the second part of the product, v squared. And we did this last time. We found the, the simpler way of writing delta v squared over v squared is going to be 2 times delta v over v. And we substitute that in for the fractional uncertainty of v squared. And then I just pulled the 2 out. 2 squared is 4. And I substituted values and got 13%. Again, I really should have rounded to 1 sig fig because we're limited by, we have 1 sig fig, is our most limiting in our product. So, I probably should have rounded to 1 sig fig, but again, it seems like it really skews the amount of the percent if I round up or down. So I kept it at 13. Anybody have any different way of doing that or want to say anything? Okay. E, how about E? Pretty similar. Does anybody have an answer for E? Maybe you didn't get to that
Did
point in
E.
your group.
Sorry, no, I didn't get to that point.
Okay,
I did E.
that's cool. We can look at what I did here. Try to think about what you would do while I'm pulling this up. Okay, so for E, I rewrote the values up there at the top. I'm now going to have basically u squared, delta u squared over u squared, and delta v squared over v squared for my 2 terms. I have a sum of u squared and v squared. So I do the square root of the sums of the fractional uncertainties squared of my 2 parts of my sum. And I'm going to convert my delta u squared over u squared to 2 times delta u over u, and my delta v squared over v squared to 2 times delta v over v, like we showed in the last step and last time in lecture. Pull out those 2's, and then I ended up pulling that 4 out, like just backwards distributive property, and substituted the values. And this time I changed it to 1 sig fig because it didn't seem too far off of the real value, which was like 19%. So 20% for this one. Try to show the whole thing. Any questions about that or feedback?
No, it makes sense.
Okay, cool. All right, now there are a couple things we haven't covered, like what about sine of theta? And like there's other things besides products and sums and quotients and differences and exponents. There are other things in math and in physics. So what if we have a function q of x? X, y, and z are measured quantities, and q is a function of x, like a times the sine of x, maybe, or I mean, whatever. Lots of different options, right? Then our general formula for the uncertainty in q, our uncertainty are in our calculated quantity based on the measured values, is going to be the derivative of Q with respect to that variable, X in this case, times the uncertainty in X. So notice the units do work out here. Delta X, this little delta X, is our uncertainty in X and has units of, let's just say centimeters in this case. And then dx is an infinitesimal bit of X. It's still going to have units of X, still going to have centimeters. So those units cancel. And then we have the same units for dq, an infinitesimal bit of Q, compared to delta Q, the uncertainty of Q. Those should have the same units as well. Okay, so questions about that? Function of X, Y, and Z. Okay, right now we're going to have it only a function of X or Y or Z, but later you might have multivariable functions. So for now, we're just going to stick to one variable at a time. Here's an example with a trigonometric function. We have Q of theta. We're just going to use theta instead of X, Y, and Z because we're doing trig. And so Q of theta is equal to the sine of theta. So based on our formula, we should take the sine of theta with respect to theta, the derivative of theta, excuse me. We should take the derivative of the sine of theta with respect to theta times the uncertainty in theta to get that uncertainty in Q, uncertainty in the function of theta. So our uncertainty in Q is equal to the uncertainty of sine of theta, our function. So that's going to be equal to the derivative of the sine of theta with respect to theta times delta theta, the uncertainty. So we know the derivative of sine of theta with respect to theta is cosine theta. And that is what we substitute here. All right, now I have big red letters down here. For problems with angles, let's use radians, not degrees. And make sure your calculator is in radian mode as well. If you're using that to do some calculations of Questions, comments? Okay. Here we have another example. Tangent of theta. Our function of theta is now tangent of theta. Theta is a measured value. We want to know what is the tangent of theta, and then what is the uncertainty in that tangent of theta. So we can write our uncertainty as the derivative of tangent of theta with respect to theta times the uncertainty in theta. The derivative of tangent theta with respect to theta is secant squared. So that's what we substitute there, and then we keep our delta theta for now in terms of symbols. If we wanted to calculate delta Q, we would substitute theta in radians, use our calculator in radian mode to calculate secant squared of theta, and then we would multiply that quantity times the known uncertainty in theta, our determined value, delta theta. Questions, comments? Okay. Now, we're going to think about the small angle approximation for a moment. Where does the small angle approximation come from?
Does it come from like a Taylor expansion, the first order Taylor expansion?
It does. It does, actually. Good job, John. Okay. And so what is the small angle approximation? Anybody?
It says that sine of theta is pretty much theta um, within, you know, a certain very small angle. So, like, I think Dr. Amay always told us that if the angle is more than like 15 degrees, then that's probably too much to use.
Okay. Cool. Yes, that's quite liberal. I've heard 7 degrees. So it just, depends on what you think of as small. But a conservative estimate of small would be 7 degrees, and a liberal Dr. Ame version would be 15 degrees. But yeah, so if our angle is small enough, sine of theta basically equals theta, and we don't even have to deal with trig. We can just say, theta. What about, are there other functions that we can apply this to besides sine of theta?
Tan of theta is also equal to theta, and cosine of theta is just around equal to 1.
Okay. And tangent of theta is equal to theta too, also, because it is sine of theta over cosine theta. So it's going to tend towards what sine theta tends toward, because that's in the numerator when cosine is 1. Yes. All right. So we kind of know, it sounds like, we definitely know what the small angle approximation is. So yes, for small angles, sine of theta is basically theta, and tangent of theta is basically theta. So yeah, around 7 to 15 degrees, which is in, you should know that in radians as well. And then it's true because the Taylor expansion. Yeah, that's where we get that from. So let's think about uncertainty in sine of theta. Maybe we can use this small angle approximation to help us with our uncertainties, make them simpler. Maybe I can use it here too. So the uncertainty in the sine of theta is cosine of theta times delta theta. And for small angles, theta is close to 0, and cosine of theta is close to 1. Cosine of theta is close to 1, like Henry was telling us. So then the uncertainty in the sine of theta, if theta is small, is the uncertainty in theta. That's a nice extrapolation of that small angle approximation. We don't have to do a sine of anything. It's just delta theta. Okay, now, is that the same case for tangent? We know that the uncertainty in tangent of theta, like we said, is secant squared theta delta theta, like we calculated in the last slide. And secant squared theta is 1 over cosine squared theta. And since that cosine is squared there, we get more deviations from what the small angle approximation tells us more quickly for tangent than we do for sine, at least with the uncertainties. The uncertainty in the sine of theta is going to be theta for small angles and for like kind of bigger angles too. But the uncertainty in tangent of theta is not going to be the uncertainty in theta for as many angles as sine. I have a table here to try to illustrate this. Calculations. Normally we would all like look at this and be like, no, I don't want to look at a table of numbers. But in this case, I just want to show you quickly that we can calculate the sine of theta, and we can calculate the tangent of theta, and the percent error based on the small angle approximation. Our percent error for theta is 36.56% down here at the bottom, where it's 13.9% for sine of theta. So if you look over this range, the percent error is bigger for our approximation of tangent than it is for sine. And same thing over here for the uncertainty in those values. So it's not, not a really big deal, but these kind of things are nice when you're doing calculations and you want to quickly get to an answer. You can make approximations, but you need to know when they're valid, when these approximations are going to break down. Okay, I need to stop now. We're going to pick back up next time with partial derivative review and the general function for error propagation. And I'm going to throw you into breakout rooms again to do some examples. So I'll stick around if you have questions.